of line codes, right? So, any one of you, is it possible to say what are the different types of line codes I have discussed? Quickly, just 2 minutes, we'll have a revision and then we'll go to the where I stopped. Yeah, quickly people should say. Yes, Kuber, can you tell? Kuber. Yes, I am asking Kuber. Kuber is there.
Yes, sir, I'm there.
Can you just mention the different types of line codes, what I've discussed so far?
Yes, sir.
Hmm? See, this is my third class. Yesterday, I repeated just line codes by taking example.
So I was not there the previous classes, but I was there yesterday, sir.
Yesterday, you were there. No? I took example and I told all the different types of line codes, right?
Yes, sir.
Hmm. You can't
I
say
remember
any one also.
Manchester encoding.
Manchester encoding. Okay. So, what is done in Manchester encoding?
So I don't remember, sir, what like
Don't
exactly.
remember. Means literally speaking, you're not concentrated anything, right?
No, sir. I was there.
Because it is one of the simple topic. Okay, line codes are very simple to understand. I understand people just log in and they do their work. Because if I am asking something very complex Fourier transform of some equation, then I understand. Okay, it is difficult to tell. But these are all very simple concepts to understand. Okay, line codes, isn't it? It clearly shows that you have not given any attention. Hmm? Okay, what about Vishal? Vishal.
Sir,
Hmm.
sir, I didn't attend the class yesterday,
You
sir.
didn't attend the class yesterday. Okay. What about Joshi? Rohit Joshi. Yes, quickly respond, man. Rohit Joshi.
Yes, sir.
Can you mention the types of line codes? Is
Sir,
it
what?
possible to say? Line codes, different types of line codes I'm asking. Yes? You can't say anything? I think you're also not there. Hmm? Hmm. Yes, what about Niharika? Niharika. Today also you're not there? Niharika. Yes, Chandana.
Yes, sir.
Yeah, can you just say what is what about line coding?
Sir, there are four
No.
types of line coding like unipolar, polar, bipolar, and Manchester.
Very good. Hmm. Yeah, in each method you can tell how do we represent binary data 0 and 1. Yes, unipolar means what? Uni means what? Single,
Um,
right?
single,
One,
single.
right? Means 0 will be symbol 0 or bit 0 will be represented by no pulse, and binary data 1 will be represented by a positive pulse having magnitude plus A volts. That A may be anything, it may be 5 volts or 3 volts, like that. Okay. So what I'm talking is about NRZ, that is non-return to 0. That is about unipolar. Then in polar means, so here we represent binary data 0 by a negative pulse having a magnitude of minus a volts, and binary data 1 will be represented by a positive pulse. Okay, that is polar. And in case of bipolar, I said binary data 0 will be represented by no pulse, and binary data 1 will be represented by alternate positive and negative pulses. Means first one will be represented by positive pulse, next one will be represented by negative pulse, like that. That is binary bipolar NRZ. Then in Manchester, I said binary data 0 will be represented by a negative pulse for half of the bit duration, and another half of the bit duration it will be represented by a positive pulse. Similarly, the binary data 1 will be represented by a positive pulse for half of the bit duration, and another half of the bit duration it will be represented by a negative pulse. So this is what the simple understanding about line coding. I think people should concentrate, give attention so that it becomes easy. If people don't give attention, then I can't help. Okay, only how much I can say. So it is your people wish to understand, learn from me. I used to say learning is learner's responsibility. Okay, so rest is yours. I cannot keep on punching again and again, submit quiz, submit OBA activity. Right, I gave 1 week time, and yesterday I have made that to uh, submit the report. I don't know how many of you have done by using LT Spice. Is it possible to say how many have tried at least? I remembered what you are supposed to do as an OBA activity. I said about PPM, right? You're supposed to do PWM and PPM using LT Spice. That is by using 315 timer. 1 week time I gave. You're supposed to submit yesterday. I don't think how many of you have really taken keen interest and learning about that and doing it. Even quiz also many are not attempting. Only 10-15 students have attempted whatever the quiz I have shared. Is what, Kuber?
Sir, can we do it on multi-sim, sir? Because we are familiar to multi-sim rather than LT Spice.
Yeah, you can do it then. Because see, you have to upgrade now. Multi-sim, yes. Means if you learn LT Spice also, where do you get LT Spice from? Analog devices, right? If you visit the analog devices, you will be knowing many things. Okay, what are their products? How relevant that company to your branch, isn't it? You will come to know many things. That is why I asked to explore LT Spice. See, every semester you need to upgrade now, right? You might have learned multi-sim in the third sem only, right? Yes or no,
Yes, sir.
Kuber? See, for upgradation only, we are asking you to explore different new tools. Otherwise, what learning the same thing, it no matter. It will take 10 to 15 minutes to do that. So when I ask you to do LT Spice, then you will visit analog devices website. You will understand many things related to even communication. So much of hardware, software, and recent trends also you will be okay. Fine. I think better try with LT Spice, even if it is taking 1 or 2 days time also, because it is similar to multi-sim only. Maybe some more upgradations will be there in that. Okay.
It's fine if we upload it within 2 days, right?
Yeah, fine.
Yes,
Hmm?
thank you, sir.
So yeah, always you should look for alternate tools. In what way these people are different and developed the things. What facilities you will get and all you will come to know. Fine, let me continue with my topic. So I was discussing about differential encoding, right? So in case of a differential encoding, what I said is this encoding technique is used to encode the information, right, in terms of signal transitions. Okay, here signal transition means what? The transition is used to designate symbol 0, right, and no transition is used to designate symbol 1. That's all. Okay, so how do we do that? I said we do the XNOR operation. So here I have taken an example. So this is my original binary data. That is what? 0, 11, 0, 1, 001. Right? This is my binary data. I do the differential encoding. For doing that, I have to take the initial bit as a reference bit. I said I can take either it is 1 or 0. If I take it 1, then I said 1 XNOR with 0 will be what? It will be 0. Right? I do the XNOR operation of these two bits. Okay, I will be getting the 0. Fine. Then 0 XNOR with 1, again it will be 0 only, right? Then 0 XOR with 1, again it will be 0. Then, hope I need not write this every time. Then 0 XOR with 0, XNOR, okay? 0 XOR with 0 will be 1, right? So, hope XOR and XNOR you are aware, right? XNOR will provide you the output when the inputs are at the same level. XOR will provide you the output when the inputs are at different levels, right? So here I am using XNOR, hence I am getting when inputs are at same level output, right? Next is 1 XNOR with 1, I will be getting output as 1, okay? Then 1 XNOR with 0, I will be getting 0, fine? Then next is 0 XNOR with 0, it will be 1, right? Then 1 XOR with XNOR, I will be getting 1. So now, how do I represent? As I said, the symbol 0 will indicate the transition, right? Symbol 1 will not indicate the transition. So with respect to my original data, I need to see. See, first 0 is their bit, right? Since initial bit is 1, I represent, means I am using a unipolar NRZ signaling, right? So unipolar NRZ signaling means 0 I will be representing by no pulse, 1 I will be representing by a positive pulse. That is why I represented here 1 by a positive pulse, the reference bit, right? Next bit is 0. That is why there will be a transition from 1 to 0, right? Next is 1 is there. Next one is there. Next one is there. So there will be no transition. Okay, only when there is a 0, there will be a transition. So first 0, there is a transition. Then next two bits are 1, 1. It will be continuing the same level. Next, again, for third bit, 0 is there. That is why, again, there will be a transition from 0 to 1. Okay. So that is why in the previous slide I said transition indicates symbol 0, no transition indicates symbol 1. Okay. Hope it is clear. Yes, people should say. See, first bit is 0 with respect to original binary data. First bit is 0. That is why the transition takes from 1 to 0. Okay, because the initial bit is 1. Next two bits are 1 1 only, right? So it will be in the same level. There is no transition. Next, fourth bit is 0. That is why it is taking transition from 0 to 1. Okay. Next again 1 is there. So it will be continuing in the same level. Next bit is 0. That is why it is taking transition from 1 to 0. Okay. And again next bit is 0. That is why again it is taking transition from 0 to 1. Right. So next bit is 1. So it will be continuing with the same level. Hope this understood. Hello.
Yes, sir.
Yeah. I said transition takes place only for symbol 0. Okay. I don't know how many are concentrating. If they are concentrating with respect to this original binary data, they should understand. Okay.
Can you
How do
repeat again, sir?
Huh?
Can you repeat again, sir?
Yeah. I said this is my original data. Okay. 0, 1, 1, 0, 1, 0, 1. Then I do the differential encoding by taking reference bit as 1. Okay. I can take reference bit 0 also. If I take 0, it will be reverse. Okay. So now I took in a reference bit as 1. Then I said what I said, I will be doing the XNOR operation. Okay, XNOR means what? When the inputs are at the same level, I will get the output as high. When the inputs are at different levels, then the output will be low, right? So 1 XNOR 0 will give you 0. Then 0 XNOR 1 will give you 0 only. Then 0 XNOR 1 will give you 0. Next 0 XNOR with 0, I will be getting 1. Okay, because the two inputs are at the same level. Then 1 XNOR with 1, I will be getting 1, right? Because these two inputs are at the same level. Fine. Then next is what? 1 XNOR with 0, I will be getting 0, right? Then 0 XNOR with 0, I will be getting 1. Then 1 XNOR with 1, I will be getting 1. Then how do I get this waveform? I said in case of differential encoding, symbol 0 indicates the transition, signal transition, right? Symbol 1 indicates no transition. So here my first bit is 0, isn't it? So my reference bit is 1, that is why it is at high level, right? So since my this one is 0, there will be a transition from high to low. Okay, now it will be 0, right? Next 2 bits are 1 1, right? So there will be no transition. It will be continuing with the same level, right? Next here, my fourth bit is 0. That is why the transition takes from 0 to 1. Okay, here that is why I indicate with this tick line. Then again next bit is 1, right? So then there will be no transition. It will be continuing the same level. Next bit is 0. Again there will be a transition here. That is from high to low. Okay. Then again next bit is 0. There will be transition from low to high. Okay. Next bit is 1. So it will be continuing the same level. So 0, symbol 0 indicates signal transition. Symbol 1 indicates no transition. That is what this differential encoding is. Hope this point is clear.
Yes, sir.
Yeah, I will go to the next one. I think I need not say again what I said, the same thing. You people can read that. Okay, next topic is regeneration circuit. Okay, so far we have discussed about the PCM transmitter. So next one is what? Regenerative repeater circuit. So this is also an important topic, and this will be asked many times for 6 marks. Explain regenerative repeater circuit. So the moment, so we use this regenerative repeater in between transmitter and receiver, right, to extend the range of communication. So what are the different blocks in the regenerative repeater circuit? It will have amplifier cum equalizer circuit. Then we have a timing circuit. Then we have a decision making device. Okay. So the input to this circuit is the distorted PCM wave, right? So when the PCM wave transmitted through the transmission line, it gets distorted, right? Noise will be added and also it gets distorted. So that will be given as input to the equalizer circuit, amplifier cum equalizer. So it does the amplification, and we all know what equalizer will do. Anyone can say what equalizer will do quickly? What is the function of equalizer? We already discussed it, na? The function of equalizer. Yes, what equalizer will do? What is the function of equalizer? Yes, quickly anyone can say the function of equalizer. You just go back, recall where I have discussed about the function of equalizer. Yes, nobody remembered? Equalizer.
So to remove aperture effect.
It will remove the amplitude and phase distortions. See, as the signal transmitted through the transmission line, it gets distorted, right? We have proved that mathematically, right? With that sync function and e power something, right? So this equalizer, the purpose of the equalizer is to remove the phase and amplitude distortions. Okay. So the output of equalizer as given as one input to the decision making device, and from the same thing we are generating the periodic pulses. So this timing circuit will be generating the train of pulses. Okay, and that will be compared with the threshold value. Okay, so decision making device is what? It is a comparator circuit. Okay, basically it is a comparator. One input to the comparator is the output of this equalizer. Another input to the comparator is the timing circuit. That is a periodic train pulses, right? So depending upon the magnitude of the output of the equalizer, this decision device will take a decision in favor of symbol 0 or 1. Okay, so if the received signal amplitude is greater than the threshold value, then this decision device will take a decision in favor of symbol 1. Okay, if the equalizer output is less than the threshold value, then it will take a decision in favor of symbol 0. Okay, this is how it generates the original PCM wave by this circuit. Okay, see, regenerated PCM wave. Okay, I will show another diagram where the pictures means waveforms are written. Okay, I hope to a certain extent you will be able to understand this. Okay, so this is my original PCM wave, which is transmitted from the transmitter, PCM transmitter, right? So as it is transmitted through the transmission line, it gets distorted. Okay, so this one is the what? Distorted PCM wave. That will be given as input to the amplifier cum equalizer. So what it will do, amplifier cum equalizer, it does the amplification, and as well as this equalizer will remove the effect of amplitude and phase distortions. Okay, then that will be given as one input to the decision making device. Okay, this is a decision making device. Then, as I said, from the output of the equalizer, we will be generating a periodic train of rectangular pulses. Okay, so the purpose of this timing circuit is to find out at what value of this equalizer the signal to noise ratio is maximum. Okay, then it will be, as I said, no, the decision levels will be there. It will compare with the decision level. Then this decision making device will take a decision depending upon the magnitude of this equalizer, whether the received symbol is 0 or not. Means accordingly it will generate symbol 1 and 0. Means if the equalizer output is greater than this threshold value, then it will be generating the symbol 1. Okay, if the equalizer output is less than this threshold value, then it will be generating the symbol 0. Okay, so that is how this is how we get the original PCM wave at the output of this. So the purpose of this is what? It will be regenerating the PCM wave. Okay, and whatever the PCM wave it will be regenerating, that will be as good as the original PCM wave. Okay, and it will extend the range of communication. So that is the purpose of this regenerative repeater. Hope I am clear. So at least you should get these three things into your mind. Regenerative repeater means it will have amplifier cum equalizer, then a decision making device. Okay, so for the decision making device, one input is output of the equalizer, another input is the timing circuit. Okay, another input is from the what? Output of the timing circuit. So the purpose of amplifier cum equalizer is what? It will be amplifying the distorted PCM wave, right? And it will also remove the amplitude and phase distortions. It will be removing the amplitude and phase distortions. Then the timing circuit will be generating the periodic train of rectangular pulses, right? At the instant of time where the signal to noise ratio is maximum. Okay, so this decision making device is nothing but a what? Comparator. It will be comparing the output of this equalizer with the threshold value, and it takes decision accordingly in favor of symbol 1 or symbol 0. So when does it takes a decision in favor of symbol 1? When the equalizer output is less than the threshold value, it will be taken in favor of symbol 0. When the equalizer output is greater than the threshold value, then it will be taken a decision in favor of symbol 1. In that way, it will be generating the PCM wave, and that PCM wave will be, means the regenerated PCM wave will be as good as the original PCM wave. Okay. So I think I can just read out what I said so far. I said the important feature of the digital system is the ability to control the effects of distortion and noise produced by transmitting a digital signal through the channel. Okay, means this digital system will have that ability to control the effects of distortion and noise, right, produced by transmitting the digital signal through the channel. Okay, so how do we achieve that capability? That capability is accomplished by reconstructing the signal, right? Reconstructing signal by means of chain of regenerative repeaters, right? And those regenerative repeaters are located at a sufficient close spacing along the transmission route. Okay, so these are the three basic functions performed by the regenerative repeater. I said one is equalization, second one is the timing, and third one is the decision making. Okay, so these are the three basic functions performed by the regenerative repeater. One is what? Equalization. Second one is timing. Third one is decision making. So what the equalizer will do, I said, it will shape the received pulses, right? So that it can compensate the effects of amplitude and phase distortions, right? So which are produced by the transmission characteristics of the channel. Then what the timing circuitry will do? It provides a periodic pulse train, right? Those periodic pulse trains will be derived from the received pulses, right? For sampling the equalized pulses at the instance of time where the signal to noise ratio will be maximum. So the samples are extracted will be compared with the predetermined threshold value, right, by the decision making device. Then, as I said, in each bit interval, the decision will be made whether the received symbol is 1 or 0 on the basis of what I said, basis of the threshold value, right? Whether the threshold value is exceeded or not. Okay. So, as I said, if the threshold is exceeded, then the new pulse will be generated. That will be what? Symbol 1, right? And that will be transmitted to the next repeater circuit. Okay. Otherwise, a new pulse that will represent a symbol 0 will be transmitted to the next repeater circuit. So in this way, as I said, we will be able to generate the accumulation of distortion and noise in the repeater can be completely eliminated, okay, by using this repeater circuit. Okay. Hope this point is clear. Amplifier cum equalizer, decision making device, then timing circuitry, right? What amplifier cum equalizer will do, you should be able to say. What timing circuitry will be doing, you should be able to say. Then what the decision making device will be doing. It is just a comparator circuit. It will take decision in favor of symbol 1 or 0 depending upon the threshold value. Fine? Yeah. So ideally, except for delay, okay, the regenerated signal will be exactly the same as the original signal, what I said, right? But in practice, what happens? The regenerated signal will be slightly different from the original signal because of these two reasons. First reason is there will be an unavoidable presence of channel noise, okay, and interference that causes the repeater to make the wrong decisions. Okay, so with that, there is a possibility of introducing bit errors into the regenerated signal. Okay, so because of this, it may be slightly different from the originally generated PCM signal. That is one reason. What is that reason? Because of what? Unavoidable presence of channel noise and interference causes the repeater to make the wrong decisions occasionally. Okay, not always, occasionally. So thereby introducing a bit errors into the regenerated signal. The second reason is if the spacing between the received pulses, okay, if the spacing between the received pulses deviates from its assigned value, right, deviates from its assigned value, means it will be taking a decision at different intervals, right? So that leads to jitter. We call that as a jitter. Okay, jitter will be introduced into the regenerated pulse position. Thereby it causes the distortion. So these are the two reasons why the regenerated PCM wave will be slightly different from the original PCM wave sometimes. Okay, so you should be able to say the reasons. Hope this is clear about regenerative repeater. As I said, sometimes it will be asked for 4 marks or sometimes it will be asked for 6 marks. So 3 blocks are there. So they will give 2 marks for each block. Okay, if you are able to say the function of each block clearly, you will get 6 marks. Yes, any doubts? Yes, you people should say, is it clear?
Yes,
Hello?
sir.
It is simple to understand what I feel, right? Amplifier come equalizer, then decision making device, then timing circuit, and even I have shown with waveforms also, right? How the distorted PCM will be, then what will be the output of amplifier come equalizer, then timing circuit, then decision making device. Okay. Fine. So this is all about regenerative repeater. The next is the PCM receiver. Okay. In the PCM receiver, the first block is decoding, right? So what is the function of decoder, right? Means we have learned how it will be encoded at the transmitter side, right? It has to do the reverse process here. That's all. There is the decoding, right? So the first operation in the receiver is to what? Regenerate the received pulses, right? Means regenerative repeater will also be there at the receiver side. Then those pulses will be regrouped into code words, right, and decoded back into the quantized PM values. So while encoding, what we have done, each quantized level we used to represent by certain number of bits, right? Then those bits will be transmitted by using binary pulses. So here it has to do the reverse process. Okay. So the decoding process involves what? Generating pulse. The amplitude of that will be a linear sum of all the pulses in the code word. Okay. So with each pulse will be weighted by its place value. We all know that, right? 2 power 0, 2 power 1, and so on up to 2 power r minus 1, where r is the number of bits used to represent per sample. Okay. I think I have shown the table, right? How each of the bits will be represented by a pulse. So that is a decoding process. So after decoding, we do the filtering, right? So this is the final operation in the receiver to recover the message signal, right, by passing the decoder output through the low pass reconstruction filter. So we use a low pass filter to get back the original message signal. So the cutoff frequency will be equal to what? The message signal bandwidth. By assuming the transmission path is error free, okay, this is the assumption of transmission path is error free, the recovered signal, okay, will have no noise. Okay, so with the exception of the initial distortion introduced by the quantization process. Okay, so what is that initial distortion introduced by the quantization process? We will be rounding off to the sample value to the nearest quantization level, right? So that will be the distortion. Other than that, if we assume that transmission path is error free, then absolutely there will be no noise added to the recovered signal. Yeah, so this is all about a complete PCM system, PCM transmitter, regenerative repeater, and then the receiver. Okay. So next, let me take up one example of that is application of PCM, which is nothing but the multiplexing, which we have already discussed about TDM, right? Time division multiplexing. Hope you're all able to recall what TDM is. Anyone can say? Any one of you can say what is TDM? At least the block diagram representation point of view. Yes? Is it not possible to visualize the block diagram of time division multiplexing? Yes, I am asking you people only. Is it possible to visualize the block diagram of time division multiplexing or not at this point of time? Yes, no response. Yes, you can't visualize. At least you should be able to visualize commutator and decommutator. Na? That is a sampling switch, right? It is an electronic switch, and those two should be synchronized. So the commutator will take a sample from each of the message signal, right? If I have n number of message signals, so those n number of message signals will be first passed through a low pass filter or pre-Elias filter, we say, right? Means we are making the signal is strictly band limited. Then we take the sample from each of those signals, then do the PAM, then transmit over the channel. So at the receiver side, again we do the, by using decommutator, we will be able to again throw the sample to each of those separate filters. Then we'll be able to get back the original message signals to the concerned receivers, right? So that is how in general we say how the TDM is. So what I wanted to say here is one application of PCM is the multiplexing. Okay, so here we will be able to do the multiplexing of different message signals with the time division, right? So each source will be individuality, means we can keep the individuality throughout the journey from transmitter to the receiver, because Each will be sampled at its own sampling rate, right? So how do I maintain that individuality? That individuality is possible with the comparative ease with which message source may be dropped or inserted in the time division multiplex system, right? So as the number of independent message sources is increased, what happens? The time interval that may be allotted to each source will be reduced. That is obvious, right? Then all of them has to be accommodated into the time interval, which is equal to what? Reciprocal of the sampling rate. So this allows this means that some allowable duration of the code word representing a single sample will be reduced, right? So pulses tend to become more difficult to generate and to transmit as their duration is reduced. It means we all know generating a very narrow pulse is a challenging task. Okay, so we can generate 1 millisecond pulse easily, but generating 1 microsecond pulse is very difficult. Means that rise and fall time circuitry is a challenge. Okay. Okay, fine. Then let me take up this example. Okay, that is the T1 system. What we say in PCM, we call that as T1 system. So T1 carrier, T1, T2, T3 and all is there. So as an example, I have taken T1 carrier. So it can accommodate 24 voice channels. Okay. And this T1 carrier system will be implemented for short distance communication within the metropolitan area. And this was introduced by Bell System, okay, in the US in the year 1960, right? And even this T1 system will be adopted throughout US, Canada, and Japan, okay, at the beginning. Let us see how that system is. So as I was telling, this T1 carrier system accommodates 24 voice channels, right? And as I used to say many times, each this voice signal is limited to a band from 300 Hz to 3100 Hz. I think I have told about 3300, like that. Yes, it is in that range. Okay, 300 to 3100 Hz. So outside that frequency band will not contribute much to the articulation efficiency. Okay, so in telephone circuitry, we use this range of frequencies only. Okay, that will give the satisfactory service. This is 300 to 3100 Hz. So as I said, each of these voice signals will be passed through a low pass filter, right? To make it each signal is strictly band limited by using a cutoff frequency of a low pass filter of 3.1 kilohertz prior to sampling. Since the highest frequency of the message signal will be of 3.1 kilohertz, we will be taking the sampling at Nyquist rate, which is 6.2 kilohertz. But in reality, it will be sampled at, as I said, 8 kilohertz. Okay, it will be done slightly higher than the Nyquist rate. Okay, so the filtered voice signal is sampled slightly higher than the Nyquist rate, so which is at 8 kilohertz. Okay, so that will be the standard sampling rate in the telephone systems. And yeah, it uses the value of mu is equal to 255, means I can say 255 amplitude levels, means the value of R will be equal to 8. Okay, so 2 power R, right? The number of quantization levels. If R is equal to 8, then the number of quantization levels will be what? L equal to 2 power R, right? Okay, so L equal to 2 power R. So it will become 250. 2 power 8 is how much? 255, yeah? 256, right? So to accommodate these 24 voice channels, it uses a binary code with 8-bit word. Okay, so we will be sampling at 8 kilohertz, and we are using 8-bit word for representing each sample value. So with that, what I can say is the data rate will be of 64 kbps. Okay, so sampling rate will be what? 8 kilohertz, and each sample value will be represented by 8-bit word. With that, I can say the data rate will be 64 kbps. Okay, 64 kbps, 64,000 bits per second. Okay, so here I have an example which I have done for this T1 system, right? So the different voice channels are combined using the TDM strategy. So each frame of the multiplexed signal consists of what? 24 8-bit words. Okay, 24 voice channels, right? In case of T1, so 24 8-bit words. Okay, so 24 into 8-bit words, and one for each voice source, plus a single bit that will be added at the end of each frame for the synchronization purpose. So in that sense, what I can say is each frame consists of what? 24 into 8, 24 voice channels, right? And each will be of 8-bit word. So 24 into 8 plus 1 for synchronization purpose. So totally 193 bits. Okay, 193 bits, right? So as I said, with a sampling rate of 8 kilohertz for each voice channel, and I can say the frame has a period of 125 microseconds, right? So 1 by 8 kilohertz will give you the frame duration, so which is equal to 125 microseconds. And in that, how many bits we are transmitting? 193 bits, right? So then I will be able to say what is the each bit duration. So I can say the duration of each bit will be 0.647 microseconds. Okay. Hope this point is clear. See, total frame duration is 125 microseconds, and the number of bits in that frame is 193. So I can say what is the bit duration. Okay. And for each channel, it will be 64 kbps, I said, right? Like the 24 channels are there. So 64 into 24 will give you the transmission rate of 1.544 Mbps. Okay, you can calculate and cross verify. Each channel transmission rate will be 64 kbps. Like that, how many channels I have? Means voice channels, I have 24, right? So 24 into 64 kbps will give you the transmission rate of 1.544 Mbps. So this is the capacity of T1 carrier system. Is any doubt among this about T1 carrier system understanding? 24 voice channels I said. Each voice channel frequency also I said, and it will be sampled at what rate I said. It will be sampled at 8 kilohertz, and each sample will be represented by 8-bit word, right? So with that, in one frame, I will have 193 bits. How do I say it is 193 bits? Because 24 channels into each channel sample will be 8-bit words, right? So 24 into 8, which is equal to 192, plus 1 bit is used for synchronization for every frame. Okay, then the frame duration is 125 microsecond. With that, I can calculate what is the bit duration of each bit. Then I said that each channel data rate will be of 64 kbps. So 64 kbps into 24 will give you the transmission rate of 1.544 Mbps. Yeah, and this is the oldest system, T1 carrier system. But nowadays, because of advancement in the technology, and they are using optical fiber, okay? In that, the T1 network will be replaced by SONET VSA, that is a synchronous optical network. In the earlier, they were using T1 carrier system. Nowadays, they are using the SONET. Okay. And I think to understand SONET frame structure and all, maybe you might have studied in DSS. Have you studied DSS? Hello? Okay. No idea. Okay, with respect to that, what we can say, the SONET will have 6480 bits. Okay, compared to T1 carrier system, will have 193 bits. This SONET frame will have 6480 bits, and its capacity will be of 51.84 Mbps. So this is what the improvement in the SONET network. Yeah, I think this I need not repeat again. What is TDM? What will be done at the transmitter side? What will be done at the receiver side is there. And I think just to get back the understanding of TDM, I have shown the diagram. You can just have a look. I said, yes, different message signals, right? A number of message signals I can have. Here it is shown in terms of packets. You can think A1, B1, C1 is one, this one. Then A2, B2, C2 is another one. Then A3, B3, C3 is another packet. Okay. Means a frame. In terms of frame, if I wanted to say, so just now I said 10 to 24 voice channels, right? With respect to that, means one from each of the channels. So here you can consider frame 1 as A1, B1, C1. Then frame 2 as A2, B2, C2. Then frame 3 as A3, B3, C3, so on. So this will be the commutator circuit and this will be the decommutator. As I said, these two has to be synchronized to get proper operation. So at the receiver side, again, it will extract A frames, B frames, C frames with respect to users. Yeah, this is another example. What I wanted to show, I don't know to what extent you are able to see this. Okay, these are all different things. It was some animation was there. Now I think I'm not able to show that animation. Yes, multiplex and demultiplex. It can take a sample from each of these conversations and feed it to the receiver side. Okay, so this is means the way different way to represent to make understand. Okay, different conversations like 24 conversations, or you can have 30 also, right? So it will be going as a frame in terms of 1 to 24. Okay, 1 to 24, 1 to 24 like that in the channel. Yeah, so this will give you an idea of all the different systems. Means I discussed only about this 1.54 Mbps, right? That is our T1 carrier system, I said. And number of voice channels is 24. So here even other systems are also there. That is 1C, 2, 3, 4 and all. That is T1, T2, T3. In terms of if I want to say, this will be T1, next will be T2, then will be T3, T4, like that. Hope this point is clear. So in case of T1 carrier system, 24 voice channels can be multiplexed. So with that, the transmission rate will be 1.544 Mbps. So like that, we can have two such T1 systems that will become T2 carrier. Okay. So with that, the data rate will be 3.152 Mbps. So we can have four, okay, a T1 carrier system that becomes T3. So with that, we can say the data rate will be 6.312 Mbps. Okay. Similar to that, higher levels, T1, T2, T3, T4, like that, it keeps increasing. So with this, I can say, I have discussed the entire thing about the PCM. Okay. So this is the first analog to digital converter, what I can say, PCM. The next one is the delta modulation. Okay. I think there are two versions of delta modulation, which we are supposed to discuss. Then there is one example. With that, I will be able to conclude this module also. Okay. Yeah. Any questions to ask? So just I took for interest different pictures from different sources. Just you can have a look. Okay. So from whatever you are able to understand, you can. So here, as I said, 30 channels, right? 24 also you can take. Then PCM, each with 8,000 samples, right? So different groupings will be done. That is TTM with 125 microseconds. How it will be transmitted in terms of frames. Have a look. Yes, any questions to ask, you can ask. You're welcome to ask. Otherwise, I will be asking the questions if I'm not getting any questions. Hope you don't have any questions to ask. Yes, you don't have any questions? Hello? Yes, Akshay Shetty, Akshay Kumar.
No, sir.
Yes, sir.
You could understand.
Yes, sir.
You take time, okay? Because that is one application of PCM. Yeah, what about Prithvi? Why man, yesterday you are not there? Prithvi? Not able to hear your voice.